Hello, my name is Dan Shiebler. I'm going to be talking today about resilient machine learning and going over a couple of different ways that we can build machine learning models that can handle the different kinds of production challenges and issues that tend to occur in the more real-world situations that we deploy our models in, and how to minimize the degree of operational load and challenges that we face when trying to build products and improve products utilizing machine learning systems. I'm currently the head of machine learning at Abnormal Security, which is a cybersecurity company. We build machine learning and artificial intelligence technology that stops cybercrime. I have a background in ML and AI. I did my undergrad at Brown, and I did a PhD in machine learning at Oxford, focusing on some of the more theoretical aspects of machine learning. I have worked at a few different places. I spent most of my career at Twitter before joining Abnormal about 2 years ago. Before that, I worked on smartphone sensor data, building machine learning algorithms to detect driver behavior at TrueMotion. And I really like the outdoors. All right, so with that, we're going to dive into the actual content of the talk today. So the first thing that I want to describe, sort of paint a picture of, is outages. This is a very common situation in software systems where there's some part of a system that goes down. And it could go down for a lot of different reasons. Maybe there's some sort of power outage or flood, or maybe there's just some engineer fat fingers a deploy, or perhaps a integer finally reaches its overflow limit, or any number of infinite reasons. And the risk of an outage expands as the complexity and size and surface area of a software system expands. And the larger and more complex your software system, the larger the probability that some part of it will fail unexpectedly at some point. And one of the challenges with building machine learning models is that when there's challenges in the data that feeds into them or in the systems that deploy them, it can be difficult to predict exactly how the model will react to these changes. And so building systems that are resilient to these kinds of changes, can handle when there's these sort of outage situations, is one of the core components of resilient machine learning. And Mike Tyson says, everyone has a plan until they get punched in the face. And we can really see the same trend in building and deploying machine learning models, where a model that we deploy may perform well in a stable situation when there's no noise and no outages, but once something occurs, it can tank the performance and cause problems. And for that reason, we need to build in layers of defense, either enabling the model to see data from outage situations during training, or deploying the model in a setting in which the model's behavior can be augmented by other systems that can correct for errors when we're in an outage situation. And so I'm going to make a kind of concrete example here of how this can occur. So I'm going to tell a quick story from when I was working at Twitter. So we had two different models that we deployed on ads ranking. So the problem here is you have a model that predicts the likelihood that a user will click on an ad at a particular point in time. And the goal is to show the user the ad that is going to have the highest likelihood that they will click on it, weighted by the size of the bid that the advertiser is placing. So it's very important this probability is very accurate, a calibrated probability. And there were two different models that we were deciding between. One model was the traditional model that had been in place for quite some time, and the other model was a newer model that had been developed utilizing newer age technology. So that the more traditional model was a continuously trained logistic regression. So it's a logistic regression model deployed in production, utilizing continuous training, where each new sample, every time a user clicks or doesn't click on an ad, that would get converted into a gradient update that would be sent to the service and update the weights of the logistic regression. Whereas the newer model was a big neural network model trained in batch on every couple of hours on all of the data that we'd seen, that goes through a ton of different cleaning processes before it is trained. And so both models were live, and we were running an A/B test, and something happened, which is that feature serving became delayed. So there's some upstream features that predict they're useful for describing the recent user behavior. So what are the things that users have seen and clicked on recently? And the pipeline that serves those features became delayed. There was either a misdeploy or an outage that was introduced by code issue. I don't remember exactly why it was delayed, but it was any of the infinite number of reasons that would cause an upstream system to serve temporarily stale data. And what we saw was that the logistic regression model immediately adapted because it's trained continuously. It quickly adapted to the fact that the new data was now older and staler, and that led to a different it's concept drift is the term, when there's a drift in the relationship between the values of the features and the value of the predictions, and covariate shifts when there's a drift in the distribution of the features themselves. In this case, we had both. So it adapted to both this concept drift and this covariate drift very quickly because of the gradient updates that it was receiving, which was able to be done scalably because this is a lightweight, simple model. Whereas the giant neural network trained on batch data, it had only ever seen data with up-to-date features, and so it could not adapt. It was a more complex model. It relied more on these temporal relationships that were now broken in the feature distribution. And so even though this model performed better in normal settings, when we had these noise settings, the performance tanks. And in a case like ads, where some bad predictions for a couple of hours could cause an advertiser to spend all of their budget in a few hours, that could be totally unacceptable behavior, which is what it was at Twitter. There's quite a bit of engineering required in order to be able to update this logistic regression to work with a neural network approach, because this batch training approach from scratch was not sufficient. So online training is one way to enable adaptation to outage situations. It's a very complex approach that has a number of other downsides. I'll talk through another approach which we utilize at Abnormal, which is utilizing multiple layers of models, each of which require different sets of features and therefore can be more adaptable to situations when certain kinds of signals are missing. So we maintain a collection of simple and complex models that consume signals from a variety of different upstream sources. So we have each sample that goes through a basic heuristic system that's just operating on the features that are directly attached to the sample. Then we have some light features that are pulled in from some lightweight data stores, and some lightweight models that only utilize those light features and these basic signals. And then we have some heavyweight models that require heavier features pulled in from heavier data stores. So these might be doing lookups that have longer I/O times, or relying on more expensive text processing, and then running into heavier models. So in the situation when the heavyweight signals are not serving for some reason, perhaps the upstream service that they rely upon goes down, or the light signals are not serving, in each of these situations, we still are able to rely on the existence of other models and other signals that are hydrated in a way that's not related to that upstream system that's breaking, building in a defense in depth against outages causing problems with the behavior of the overall system. So essentially, since the different components of the engine rely on different upstream signals, the overall engine is resilient to system failures and outages. So the next thing I want to talk a little bit about is adversaries, which are a particular kind of challenge that machine learning systems need to be resilient to. This is particularly poignant at Abnormal Security, where we are a cybersecurity company. As a cybersecurity company, there are adversaries who actively attempt to break our models, to identify where there are chinks in our armor and pass through them utilizing attacks. And so it is critical that we build our models in a way that's adversary resilient. and aware of the kinds of strategies that adversaries may apply and resistant to them. So I'll talk through 3 general categories of strategies here, and then I'll go a little bit more into some of the specifics. So the first is high variance behavior. So high variance behavior means that you build your model in a way where there's no single general exploit that will always work for the attacker. And so an example here is user-specific model components. If you have a model that behaves differently for every individual user who protects. So for us, for instance, we have email security models that detect when there's different kinds of malicious attacks that attackers are attempting to deliver via email, maybe malware or phishing. And we have model components that utilize the features of the users themselves and have a very high influence on the behavior of the models. So this means that if an adversary is able to identify a particular kind of attack that allows their attack to get past our models for a particular user, that attack may not be generalizable and likely isn't generalizable to other users because of the high variance behavior of the models across different users, because of the dominance of those user features and the overall behavior of the model. So this gives the models a defense in depth. If that adversary attacks multiple users, for instance, now we can leverage the fact that we've caught the attacks of some of the users to protect it from other users and not just rely on a model that may have failed on certain ones. So high variance behavior serves as the foundational armor to building a system that is resilient to targeted attack, especially from attackers who are testing their system, testing their exploits against your system directly. So the next insight is to utilize multiple uncorrelated predictions. And we could think about this as having multiple layers of defense, each of which have different weaknesses. And this enables individual exploits that may work at a particular layer of defense to not work for other layers of defense. And let me give you a concrete example here, which I think is really relatively illuminating. So when we do natural language processing, one of the critical decisions that we make is how we represent the text that we are passing to the model. And there's a number of different ways to do this, but fundamentally there's 3 broad options. One option is that we could use words. We could represent our tokens as individual words, utilize a large vocabulary, and any word that doesn't fit in our vocabulary is represented with some out-of-vocab token. The next extreme is to utilize characters. We could utilize each of the individual characters of the text and pass that into the models directly. So in this case, there are no out-of-vocab because the character set is relatively small, but there's a larger degree of complexity and that the model needs to learn in order to understand characters. And then in between the two, we have word pieces, where basically we identify groups of characters that co-occur frequently in the sort of words that are in the type of text that you're trying to work with. And this is generally considered the optimal approach in modern natural language processing. This is the approach taken by almost all large language models, for instance, to utilize a word piece-based approach. All 3 have weaknesses. The word level and word piece level have weaknesses if the attacker is able to understand what your tokenization vocabulary is and make targeted changes to the types of language that they're utilizing to force out-of-vocab tokens and force the model from missing the content of their text because of a flood of out-of-vocab tokens in a way that an end user may still recognize. So this is a kind of natural language processing attack. However, that approach won't necessarily work on character tokens because you can't force an out-of-vocab. On the flip side, adding lots of noise characters in a text attack will reduce the ability of a character level model to identify relationships between different parts of a word or different parts of a sentence. But that won't work nearly as well for a word piece model or a word level model that will likely take the noise character tokens and represent them all as out of vocab and not pay attention to those and only pay attention to the actual relevant parts. And so these 2 different approaches that attackers might take might pass one but not pass the other. And so for this reason, at Abnormal Security, we utilize text models that utilize all three different kinds of tokenization strategies in order to define a defense in depth approach that protects against a number of different attacker exploits. And so the last element is automated adaptation, which we could think of as a few different things, but the easiest way to think about this is automated retraining. Whenever we make a miss, or whenever we see new data, we want to incorporate that data into our model as quickly as possible, so that our model in the future is able to make the correct decision when it faces a similar type of attack. So what I'll talk about next is a general model design paradigm that enables us to build models that are more resilient to adversarial attacks. And we can think about this to begin with. Think about the problem of finding a needle in a haystack. And there's sort of two ways to build a detection model that can identify the needle in the haystack. One way is we build a model that really, really clearly elucidates what a needle looks like. And so we check each piece of hay, compare it to this model. And once we find a piece of hay that's actually looks really, really similar to a needle, we say, okay, we found our needle. The other approach is to model really, really well what all of the different kinds of hay look like. And then when we find a piece of hay that doesn't look like any of the pieces of hay that we thought it was supposed to look like, we say, okay, now we found our needle. And when we think about both of these are valid approaches, but when we use the latter approach, when we model what hay looks like, it's harder for an attacker to add the characteristics of hay to their needle than it is for them to modify their needle in a way such that our model of a needle may not be a good match, especially if we're working with just a set of needles and we're trying to build a model that represents the set of needles we've seen in the past. If the attacker is able to come up with a new shape of a needle that doesn't match any of the shapes of needles that we've seen in the past, then we're vulnerable. Whereas if the attacker is trying to simply match the shape of the hay, it's very difficult for them to do that in a way that preserves the needle characteristics. And so we're defended against different kinds of modifications that the attacker may make to the shape of their needle. And to make this a little bit more, bring this a little bit back to earth, we can think about this as there being easy to impersonate signals and harder to impersonate signals that are foundational to how we build systems that fight adversaries. If we include both and allow our model to pay a lot of attention to these easier to impersonate signals, we may build a model that's easier to fool by an attacker who's able to mock those signals. If we force our models to pay more attention to the harder to impersonate features, or ship some models that only utilize those features, then perhaps we'll give a performance on the median case, but the model will be harder for attackers to exploit. So here's an example for social media. For example, we can fool relatively easily signals like click-through rates. Attackers can build really clickbaity content. However, it's much harder for attackers to fool spam reports. So utilizing signals like spam reports or conversion rate, which is much more indicative of quality content than click-through rate, as signals that we incorporate into a spam detection model, build something that's much harder for attackers to fool. And in the cyber attacker worlds, we can think about things like the sender reputation or the strangeness of this particular message for this particular recipient. This is something that is very difficult for an attacker to mock because both of these require spending a good deal of time building these reputations or understanding what the recipient's message distribution is. This is much harder to mock than simply creating a new link or modifying your vocab in the email that you're sending, which will make it so that a pattern matching system that's matched just directly to the bad attributes will fail. So the next phenomenon I want to talk a little bit about that can cause challenges in production machine learning systems is feedback loops. So fundamentally, when we launch a machine learning model to production, we run the risk that that model's behavior may impact the behavior of our system in the future and may impact the behavior of the model in the future. This kind of feedback loop can be very nefarious in how it can slowly degrade the quality of our system without us fully understanding how or why. And one way to characterize this is to think about the flow of data. So let's start here with a model that we have and that we regularly retrain. And we can see our model generates predictions. These predictions impacts the production system. Maybe this model is ranking tweets on the timeline. Maybe it's identifying spam emails. Maybe it's identifying malware. These predictions then affect the user experience. It affects whether or not the user sees that tweet or receives that email or has that file removed from their system. That user then takes actions. Maybe they click on the tweets, maybe they download a file, maybe they respond to an email. These actions are then utilized to do multiple things, including form our training data that we're utilizing to retrain the model in the future. Maybe we are training our tweet recommendation model based on the tweets that users clicking on. So this action directly adds positive samples to our training data. And it also affects features. Maybe the user submits a spam report, and one of our features is the number of spam reports that a user has received or a sender has received. And then these feature changes will then percolate into the features that are used the next time the model predicts. And this data now is incorporated into the next retraining of the model, which will once again impact the predictions that the model then generates, thereby creating this feedback loop. We need to be very careful about how this feedback loop is constructed such that it can impact what types of new data is being received and whether or not that data is representative of the distribution that we want the model to perform well on. If, for example, we're only getting labels on samples that are less important, we could see slow degradations. And so here's a concrete example from abnormal security, where we have an email. That email flows to our model. That model either predicts attack and removes the email, or predicts safe and delivers it. What we can see is that there's 4 cases. So let's say we predicted an attack and it was actually safe. In this case, we might get a label because the end user may end up correcting our judgment. If there's a security team who gets notified when we detect an attack, and perhaps they say, no, you were wrong, and they correct it. And if we were correct, we likely get no label at all because nobody will validate the fact that it was correct. And it's sort of the flip side on the safe side. If we are correct, then the email will be delivered. We get no direct label. And if we're incorrect, then perhaps we'll hear about it if there's an end user report, and so we may get a label that way. And so in this way, we have this flow of data that we hear about mistakes potentially, but we don't hear at all about the cases where we believe that we're confident. And so this is not a terrible feedback loop because generally mistakes are the types of data that we most want labels on. But this does heavily bias the kinds of training data that we have and make it very difficult, especially to capture how to reinforce the existing model's behavior in a high confidence way by taking advantage of these true attacks that the model is catching and identifying the value of those when retraining the model and percolating these labels into the features that are utilized for future predictions. There's a few different ways that we can break feedback loops. And so I'll just walk through one strategy here, which is to utilize sampling. So we could think about this as we have live data. This data feeds into a system. That system has impacts, and that impact goes into our database. And what we can do is we can sample that data that's being generated and passed into our system and have a separate path by which certain samples that are selected are chosen for labeling, outside of what kinds of labels our system by itself may generate. And so this is a very sort of simple path. All we're saying is, well, we're actually going to choose which samples we label rather than just letting the system label it for us. But in certain kinds of contexts, this can be quite tricky to do appropriately. For example, on Twitter, the number of tweets that somebody could realistically label is much, much smaller than the number of clicks on actual tweets that we would serve. So we need to be very careful in selecting how exactly do we choose the samples that are most valuable to select. And so there's a couple of different algorithms for this, but one that's particularly useful is importance sampling, where essentially we weight each sample by its inverse probability of appearing, and then we sample the individual samples that will give us the most information for reconstructing our serving distribution. And utilizing an algorithm like this enables us to get an unbiased sample set that we can then utilize to train our models and break feedback loops. This usually is not sufficient as an overall training strategy, but it does allow us to have an unbiased stream to train certain types of models that require less data, to utilize as evaluation between multiple different kinds of models that are trained with different weightings over the base training data, which can be just as good, and for serving as a sanity check as well. So the last thing I want to end with is just to say that this is a very challenging problem. As machine learning engineers and data scientists, there's a great deal of challenges that we need to face. And many of these challenges don't fully appear until we're facing them down in a production setting. And so I hope that today's presentation helps equip you with the weapons that you need to defeat your enemies. Thank you very much. We have a few minutes if you have any questions. All right, so one question is on automated adaptation, which I'll talk about. So there's really two different ways to have adaptation. So one is to adapt the model weights, and the other is to adapt model features. So adapting model weights is pretty simple. We just have some sort of stream by which we get labels. Those labels, maybe they're like by misses, like we were describing a moment ago in the abnormal security label stream case. And we retrain our models with labels that we've received, and that enables the model to behave better and differently in the future. And so that's one way to do a pretty straightforward automated adaptation. One of the downsides to this is that retraining a model is a very involved process that has a lot of risk. You might forget what the model was doing in the past, for instance. And so another way to do it is to instrument this at the feature level. So one thing that we could do there is we could take some sort of extractor that extracts like indices from the samples that we're processing. So at the level of an email, this would be things like the from email, the links in the email, etc. And then we have a feature that looks up these indices and looks up what previous judgments on these indices were. And so if we see one email that is marked bad, then when any future email it gets processed, we look up what was the history of judgments that we've had on emails that share the same sender, share the same link, share the same kind of vocab, share the same types of IP addresses, any of the different things we extract from this email. And in that way, each sample that comes through actually changes these features, these like sort of history features that we have associated with each of these indices. And so these are sort of the two different flows, the feature level flow and the weights level flow that enables us to automatically adapt to mistakes the system makes. All right. Well, thank you, everybody, for joining me today. Looks like we're out of time. I hope you have a nice evening.